Hello everyone. Welcome to Chapter 7, Solutions. A solution consists of a solute and a solvent, and can sometimes consist of more than one solute. But solutions are homogeneous mixtures, meaning that you can see through the mixture. There's no distinguishable parts, and it consists of two or more substances. And it forms when there is a sufficient attraction between the solute and the solvent, and we'll talk about that a little bit more here on the next slide. There are two components, the solvent, and this is what's usually present in the largest amount. So water is a very, very common solvent, and it's present in the largest amount, and it actually dissolves the solute. The solute is usually present in smaller amount, and it is what is being dissolved. So if we look here, we've got salt water. So the salt that's coming into the water in the beaker, we would stir this, and the water would be our solvent, and the salt would be our solute. And as we would stir this, we'd be able to dissolve the salt up to a certain point, and it would be a homogeneous mixture or a solution. Okay, so solutes will spread evenly through the solution. These are not distinguishable parts, so they cannot just be separated by filtering. So you couldn't just pour it over filter paper and the distinguishable parts be able to just sit on top to be separated that way. However, you can separate the solute by evaporation. So thinking back to our salt water, we could put that salt water on a hot plate and boil the water off, and then in our flask we'd be left with the salt. So by evaporation you can pick apart or pull out your solute. Solutes are not visible, but they can give color. So don't confuse color with distinguishable parts, okay? Here is a copper solution, okay, and it turns blue, so this is still a solution. Okay, clear doesn't mean that it has to be clear. It can have color, but it is still a solution because you can still see through it. There's no distinguishable parts. Just like if you had vegetable soup, for instance, you could pull out the potatoes and the peas and whatever else is in there. Well, for a solution, it's not that way. You can't pull apart the parts. It looks like a homogeneous and clear, you can see through it mixture, but it can have color. So there's all different types of solutions. So we can have a solid, liquid, or a gas as a solute or as a solvent. So this just goes through and gives some examples, even ones that we haven't maybe heard of, but if you look down here in a liquid and a solid, this is actually like a filling for your teeth. So at the dentist, if you get a filling, it could be made of mercury, which is liquid, and silver, which is solid. Okay, so that's kind of a unique example. Also, a solid and a solid. Brass is made up of zinc and copper, so those are two solids that are basically they're soluble in each other. Another example, so a gas and a liquid. Your soda drinks that you drink, or some of you may or may not drink, I do, but the carbon dioxide gas is what makes your soda fizz. And the gas is what's trapped in your can or your bottle with the water or with the sugar or whatever else is in there as well. And so this will be an example of the gas soluble in a liquid. Okay, the air that we breathe is primarily nitrogen and oxygen. So nitrogen would be our solvent because it's present in the largest amount. Water is one of the most common solvents in nature. It's polar, so you want to think back to when we talked about bonds and electronegativity. So be sure, if you haven't to this point reviewed electronegativity, what that means. Look back at your polar covalent bonds, nonpolar covalent bonds, and your ionic bonds. Okay, because this is going to be important with respect to solutions. Okay, water is polar. So one thing to remember right off the bat is that water is polar, and the reason for that is due to electronegativity. So if you guys remember me saying, I think I did in a video, I tell my students in lecture class all the time that I love the word electronegativity because we constantly come back to this term. Okay, and this term means that is the ability of an atom to attract electrons to itself. Okay, electrons are negatively charged. Okay, so if we look at water, we have a partial negative charge on our oxygen and a partial positive charge on our hydrogens. Okay, reason being, okay, fluorine is the most electronegative element. So look at your periodic table. Okay, and if you move away from that, oxygen is close by. Oxygen is more electronegative than hydrogen. So basically it's winning the tug of war. It can pull harder on those electrons, and it pulls them basically away from the hydrogen in this covalent bond. Okay. Molecules form hydrogen bonds. Okay, this is what this is actually showing here. We talked about this briefly in one of the previous chapters. But hydrogen bonding is what makes water have such a high boiling point for a pretty low molecular weight compound. And so I'm just going to redraw up here that you have a partial negative and partial positive. So there is an attraction of this partial. So this little dash here, this is called a hydrogen bond. Okay. And it's going to be attracted, remember opposites attract, it's going to be attracted to the partial positive charge on another water molecule. Okay, it will be where your hydrogen is. Okay, and the same would be true here. So we could have another hydrogen bond. So we have a partial positive charge. If opposites attract, then which atom, if we have another water molecule, is the oxygen or is the hydrogen going to be attracted to the hydrogen? Okay. Yes, you are correct. It's going to be the oxygen because opposites attract. The negative charge is going to be attracted to the positive charge. And these are not, even though they're called hydrogen bonds, I don't really like that term because they're not true bonds. They're attractions. But these are strong attractions. And so while you're waiting for your water to boil, when it's on the stove and you're trying to boil something, you are actually waiting for these hydrogen bonds to break. And that is why water has a higher boiling point than you might expect. Okay, we're going to talk about ionic and polar solutes as well as nonpolar solutes and solvents. And the key here before we even get started is we want to remember that like dissolves like. Okay. And this means that polar solutes dissolve in polar solvents, and nonpolar solutes, just going to abbreviate here, dissolve in nonpolar. Okay, so I want you to remember this. And this is really the key, but we're going to go through and show why this is, but this is the key. If something is polar, first thing you have to know whether the compound is polar or not. You got to be able to determine that. Okay, so you want to remember that ionic compounds, okay, this is a metal and a nonmetal, so be sure you go back and look at what an ionic compound is, polar, covalent, nonpolar. Okay, is polar. These are very polar because they have a large difference. So that's a change, that just means difference in electronegativity. So here we are again discussing electronegativity. A metal from one side of the periodic table, the nonmetal from a different side of the periodic table. So they have a large difference in electronegativity, which makes them very polar. Therefore, something like NaCl, sodium chloride, this is an ionic compound, it actually undergoes hydration as water molecules will surround the ion and pull it into solution. So water is a good solvent for sodium chloride. But this just isn't a coincidence. It's the fact that water is polar and sodium chloride is polar as well. And due to this fact and the charges and the interactions that there are between the salt and the water, you're able to dissolve salt in water. Okay, and so what actually happens here, so we would show this, if we represent this with an equation, we would say that NaCl in water will dissociate, that's what we used here, to its constituent ions of Na plus and Cl minus. Okay, remember, sodium is in group 1, so it has a +1 charge, and chloride is in group 7, meaning it wants to gain one more electron to be like the nearest noble gas, so it has a -1 charge. Okay, but what actually happens in solution is this positive charge on the sodium is going to be solvated by the negative charge. So there's an attraction here between that negative charge, or the partially negative charge, on the oxygen. So the water is actually able to go into a crystal. Remember, crystals are rigid, so ionic compounds usually have strong melting and boiling points, or high melting and boiling points. But if they have a polar enough solvent, it can go in and be attracted to the charge. So here we've got oxygen going to be attracted to the sodium. Okay, for our chloride, we have a negative charge. So the hydrogen portion, so our partial positive charge, is what's going to solvate. You can think of it as it encompassing, or it's pulling those ions apart. Okay, and so when you separate the ions, it becomes soluble. So the key here, like dissolves like. Polar solutes dissolve in polar solvents due to this interaction of solvation, where you have positive charges interact with negative charges, opposites attract with respect to the charge, and then you have this negative charge from your chloride, and you have a positive charge from your sodium that you're able to dissociate and pull apart into the separate ions to be soluble in water. And that is due to the fact that water is polar, and it can do this. It can solvate, or it can hydrate, is the better term here. It can hydrate those ions and basically break this apart. So it has to break apart the crystal in order for it to be soluble. So this just shows, once again, that polar or ionic, your ionic compounds, metal and nonmetal. Okay, and then so sodium chloride, potassium chloride, sodium bromide, and the list could go on. And we have to have a polar solvent. So this is just a table showing like dissolves like. Okay. A solution will not form if you have the opposites. If you have polar and nonpolar, solution will not deform. If you have a nonpolar solute and a polar solvent, a solution will not form. They will not be soluble in each other, and a solution, homogeneous mixture, will not be present. Okay, so this is just an example showing this. So here you can see we've got two distinct layers. So if you were in lab and you put two solutions together, or two compounds, a solute and a solvent, and you saw two distinct layers. Okay, this is not a solution. These are not soluble. Okay, so you've got two separate layers. So this is what this is talking about, that if they will not dissolve in each other, then they're going to form two distinct layers, and these would be, so if you had a polar and a nonpolar compound, they're going to separate. Okay, a solution is not going to form. Okay, this example would be an example of a solution. And let's say that two compounds are represented in here. We're not sure if they're polar or nonpolar, but they would have to be a polar solute and a polar solvent. or vice versa. You could have nonpolar and nonpolar. You have a nonpolar solute and a nonpolar solvent. Okay, if you have a polar and a nonpolar, then you're going to see this separation, and the two are not going to form a solution. Okay, let's go through and identify the solute in each of the following solutions. We have 2 grams of sugar and 100 mils of water. Okay, our smaller amount here is the sugar. It's going to be dissolved by the water, so the sugar would be the solute. We had 60 mils of ethyl alcohol and 30 mils of methyl alcohol. This is the lesser of the two. Our solute present in the smallest amount. We have 55 mils of water and 1.50 grams of sodium chloride. Okay, sodium chloride is going to be our solute that dissolves in the water. In air, we have 200 mils of oxygen and 800 mils of nitrogen, so we have less oxygen, so it's going to be the lesser amount. Okay, so this just shows our answer. So we said sugar, and methyl alcohol, sodium chloride, and oxygen. Okay, if we were to look at lithium chloride in water, we want to discuss why lithium chloride will form a solution with water. So if we look at lithium chloride, and if we placed it in water, it's going to dissociate to lithium plus. Okay, it's in group 1, so it forms a +1 charge, and chloride's in group 7, so -1 charge. It wants to gain 1 electron to be like the nearest noble gas. Okay, so if we have water, we know that our oxygen is partially negative due to electronegativity. So our water looks like this. Our hydrogens are partially positive. Okay, and so this is asking us, solid lithium chloride is added to water. It dissolves because of why? So this is going to go back to our attraction between positive charges and negative charges. Okay, what's going to happen? We have a negative, so opposite charges attract. We have a partially negative charge on the oxygen, so the water is going to solvate the lithium. So there's going to be, thousands of water molecules. So we're just showing one here. We would have oxygen. Here's another one. So it would be, we're going to solvate it, or we're going to hydrate it. So we could keep drawing these. The main thing to see here is that that negative charge on the oxygen is going to be attracted to the positive charge on the lithium. So we could keep drawing that, and this would be known as hydration. So it's able to break apart the solid lithium chloride. And then it's going to be opposite for our chloride. So if we look at chloride, the negative charge, so our partially positive hydrogen is going to be hydrating the chloride. Okay, and so we could continue and we could draw more and more of these. Okay, all around, and this would be hydrating the chloride. So if we look at our answers here, the lithium ions are attracted to, so there's an attraction between the positive charge and the partial negative charge on the oxygen atom of the water. The chloride has a negative charge, so it's going to be attracted to the partial positive charge of the water. Okay, just a few more things to note here. You want to be sure that you know what's polar and what's nonpolar. Okay, we've just discussed in detail ionic compounds are polar. Okay, we've looked at water. It's a covalent, but it's a polar covalent compound. So you want to be sure that that you know those. But let's go ahead and just label these. Okay, we're going to look at A, B, C, and D, and we're going to talk even a little bit more in detail about these. Okay, if we look at Okay, we've got sodium sulfate. We have a metal and a polyatomic ion that has a negative charge, like this. So this is ionic, very similar to what we were just looking at. It has a metal and a non-metal portion. This ionic, which we know is polar. Okay. Here we're told that gasoline is nonpolar. Okay, so you're told that. But you also want to know that hydrocarbons, okay, basically anything that consists of only hydrogen and carbon are considered to be non-polar. So examples, methane. Another example would be this. Okay, so if you see a compound that only consists of carbon and hydrogen, so this is super, super important that you remember this, that it is considered to be nonpolar, even though there's a very, very, very small difference in electronegativity, it is still considered to be nonpolar. Okay, when we have our twins here that look identical, so our two iodines, they have zero difference, so zero change in electronegativity, so they're considered to be nonpolar. These are actually nonpolar covalent compounds. Okay. So we have HCl. There is a difference in electronegativity. This is a polar covalent compound. Okay, it's polar because hydrogen and chlorine have a difference in electronegativity. It's not ionic because we have two nonmetals. So remember that covalent compounds are nonmetals. Okay, ionic compounds are a metal and a nonmetal. Okay. So now that we've gone through and looked at these and determined if they're polar or nonpolar, that's the key. Because it asks us to tell whether these solutes will dissolve in water. Okay, key here is we have to know that water is polar. Okay, and we know that like dissolves like. So if we know if a compound's polar or not, we should be able to answer the question. So if we go through A through D, the only compounds that are going to be soluble in water, because water is polar, are the polar compounds. So we labeled A as polar. It's an ionic compound. Go back and look at your polyatomic ions and convince yourself that that's the sulfate, got a negative charge. Okay, gasoline, nonpolar. C, iodine, nonpolar. D, polar. So A and D would be solutes that are soluble in water. Due to the attractions between the positive and the negative charges, but you can also, without showing all that, you just have to figure out what's polar, what's nonpolar, and then what's your solvent. So if your solvent's polar, then you go through and you circle everything that is polar. This concludes the video for Chapter 7.1.